Okay, this is lecture 4. Due to my business trip, I record this lecture 4 before I start my business trip. Okay, so let's go to this one. Okay, today's lecture content is MOS capacitor. So please try to remember our previous lectures. So lecture 1 was devoted simple instruction set. So we just saw that how can we program a simple calculator. After that, the essential part of this calculator was logic, and the logic is implemented with CMOS, and CMOS contains both of N MOSFET and P MOSFET. Then how can you describe their behavior, electrical behavior, in the level of compact modeling, so circuit simulation? So that was discussed in our previous lecture too. After that, we have studied how can we solve a nonlinear equation originated from certain um, physical constellation. Then we have found that this is quite powerful to solve a nonlinear equation. So today's lecture, lecture 4, is devoted to a certain physical system called as MOS capacitor. So we will find that actually the physical equation for MOS capacitor is a certain nonlinear equation once again. So we have certain nonlinear equation for a certain quantity called as a surface potential. So we wanted to solve this nonlinear equation. Then by using the technique we have studied in lecture 3, Newton method, we can solve this nonlinear equation so we can calculate y s at a given condition. So from the viewpoint of numerical technique, so today we have no new material. However, instead of that, we apply this already known technology or technique to MOS capacitor. Since MOS capacitor is so important in our actual study, so it means that lecture 4 is also important for our further study. Okay, let's go to this MOS capacitor. So although this is the very first time to think about MOS capacitor in our lecture, Computational Microelectronics, but I assume that you have already studied this MOS capacitor several times. For example, if you are in the junior level semiconductor device course, you already know the MOS capacitor. And if you go to the senior level study once again, then there you learn this MOS capacitor once again with a much more advanced way. Even in your microelectronics course, usually taught in your sophomore level, still you have MOS capacitor. Although the level of presentation is somewhat different between these lectures, but anyway, I assume that you have already studied MOS capacitor. Okay, so this is a problem specification from the viewpoint of our lecture course. In this case, instead of considering all kinds of physical meaning, we just treat it as a equation. So here we have oxide layer, and how thick is it? Right now it doesn't matter. So anyway, the interface between oxide and silicon is located at a position of x equal to 0, and p-type silicon is semi-infinitely long, so it goes to the infinite, positive infinity, and beyond a certain position, for example this position, then everything is just homogeneous. So for example, the electrostatic potential or electron density and hole density, beyond a certain point, everything is just uniform and homogeneous. Okay, so now we introduce a certain quantity called as electrostatic potential, and also assume that our two important quantity, carrier densities, electron density and hole density, follows this relatively simple form. The important point is this is just or these are just linear local equations. So the electrostatic potential at a certain position immediately determines the electron density. The same quantity also immediately determines this hole density. Of course, I want to say that these two equations are not generally valid, but they are valid at equilibrium case. In equilibrium case, we can sufficiently um, assume that these equations hold. So please uh, accept these expressions for a while, and we believe that electrostatic potential is a function of position, and we have a certain well-defined behavior of our electrostatic potential. That is our assumption. Okay, then our next goal is how can we determine this electrostatic potential? If we understand this electrostatic potential, then by using these two relations, then we can also immediately calculate electron density and hole density. So this electron potential is the central quantity of our analysis. Okay, then so although phi can be defined all over our x position, so starting from 0 and expand up to positive infinity. However, most important one to our purpose is the one at uh, x equal to 0. So we wanted to know this quantity. Of course, if we know this quantity y at x equal to 0, then that does not necessarily mean that we have full information about the form of electrostatic potential inside this system. But anyway, to us, the most important one, the most important quantity is the potential at x equal to 0. More precisely, instead of this electrostatic potential itself, we wanted to know the difference between electrostatic potential at interface or at surface and at the deep substrate. So this one is used as reference value, and this one is just a measured value. And since this notation is too frequently used, so usually when we say surface potential, it is assumed that the deep substrate is the reference of this quantity. Okay, so for example, let me just give you a certain example. Let's say that at x equal to 0, assume that phi equal to positive 0.3 volt. And let's assume that also when we go to the deep substrate, then happen to be phi equal to minus 0.4 volt, for example. Then in this case, what is the surface potential in this notation instead of this 0.5 measured at the surface point? But we have to say that our phi sub s, the surface potential, is equal to 0.9 volt because we have to do certain operation like this, and we have a 0.9 as a result of this operation. Okay, so are you with me? So please note that in our notation, surface potential is always referencing the potential at the deep substrate. So then, what is this reference value? So here I have made some summary on the values at the deep substrate. So in this case, at the substrate, so we believe that since everything is so uniform, so although this is a certain position, for example 10 micrometer, and this is 20 micrometer, however everything is just the same, no change in their physical quantities. So we have to say that since there is no change in spatial constellation, so here and there, each of them is in its local equilibrium. Local equilibrium means that the electron density and hole density is purely determined by our dopant density, the local one. The local dopant density really determines electron density and hole density. Then how can we understand this condition? So from this local equilibrium conditions, we further develop charge neutrality condition. So this is assumed, and it means that sum of all charged carriers should be 0, or the sum of all charged carriers density should vanish. For example, here we have acceptor density. Acceptor density, acceptor is negatively charged, so we have to consider acceptor density minus. Then how about hole? Hole is positively charged, so we must have hole density here with the positive side. And how about electron? Electrons are negatively charged, so we must introduce a minus sign. The sum of these three quantities with weighting factor of their own charge, then it should be vanishing here. Then it means that the net charge density vanishes and everything is just consistent. So from this one, we can write down in this way. Na should be balanced with P minus N. And that condition is just written here. Na equal to, what is it? This is corresponding to the hole density evaluated at a substrate point, and this quantity is corresponding to minus n evaluated at a substrate point. So please note that here we have n int, and you know that this is corresponding to intrinsic carrier density. Of course, this quantity is dependent on the temperature. For example, in the case of a silicon, if we have 300 Kelvin, then intrinsic carrier density would be about just 10 to the 10 per cubic centimeter. So we will treat this intrinsic carrier density as a known material parameter. So we do not care about it any further, and our goal is just to calculate electrostatic potential. And another condition at the deep substrate point is the electric field vanishes at the substrate. So if we calculate the phi over dx at a substrate point, then that should be vanishing. So it is quite reasonable. For example, let's have a look at a model electrostatic potential profile. And here you can see that everything is just uniform independently on the position coordinate, and when you take d phi over dx here, then of course it vanishes. So okay, so simply speaking, up to now we have introduced certain equation. Oh, so so up to now we have introduced the boundary conditions for this x equal to positive infinity point. And we wanted to know the quantity at this surface point, and the remaining question is then what is the governing equation for the points between these two boundary points. That will be explained in the next slide. The answer is the Poisson equation. We must solve the Poisson equation for the domain semiconductor, the domain, and it is shown here. Yes, this is the Poisson equation. The second derivative of our electrostatic potential should be matched to the net charge density. For example, here this is corresponding to the net charge density, and with a certain permittivity function, and here negative sign, we can have the Poisson equation. So if you are not much familiar with Poisson equation, then please leave your previous lectures on the semiconductor device. So I will not dive into the meaning of this Poisson equation. So let's review this Poisson equation from our viewpoint. So in this case, now we treat this electrostatic potential as a unknown variable, and Q and epsilon, they are given numbers. And here we have a hole density and electron density, but they are right now just treated as two nonlinear functions of phi of x. The electron density and hole density at a given position is are nonlinear functions of the electrostatic potential evaluated at that position, and this is just a constant. So now you can treat it as an equation for electrostatic potential. Okay, so that's the reason why, although we have three unknown variables: electrostatic potential, hole density, and electron density, but they can be just unified only as the electrostatic potential. Okay, so then uh, here we have a very important step to further development. This is quite important, so and very specific for this problem. Instead of considering the Poisson equation itself, in this case we just multiply this factor to the left hand side and right hand side to keep the balance. Then what happens in the left hand side? Now we have second order derivative and d phi dx and dx, and it can be treated as combining this and that can be treated as d phi dx, and here we have a remaining d. Yes, this is d phi over dx, that is shown here. And how about the right hand side? Also this one can be just treated as a d phi, and you can see that here we have a d phi. So you know that although it looks complicated, this is nothing but of the Poisson equation multiplied by this simple factor. Okay. Why do we bother with why are we bothered with this complication? So it will become clear later. It gives us quite much simplification of the problem. Okay, looks quite complicated, but now let's move on. Here, left hand side term is just kept as before, and from here to there, we wanted to eliminate this NA variable because NA is just a constant, so it is not that good for integration. So what we do is just to observe what is NA. So from the boundary condition for electrostatic potential at the deep substrate, now we have the expression for acceptor doping as a sum of these two terms, actually hole density minus electron density. Yes, so we can just insert this expression, then yes, we can just consider this expression. After that, combining them all, well, we can easily make it this way. Here we have long expression and here intrinsic carrier density. Okay, you know that this term is originated from this one, and this one is originated from this one. And how about these third term and last term? They are coming from the expression for our NA. Well, then in order to make it simple, so we introduce a simple intermediate variable or the electrostatic potential referenced to the substrate. What is it? This is nothing but just the quantity. Of course, in this case, position is fixed to 0, but if we just generalize it, then we can define the electrostatic potential referenced at the substrate. So in this sense, our surface potential can be just written as phi bar evaluated at x equal to 0. I think that maybe uh, somewhere I have already shown this relation. But anyway, let's introduce this intermediate variable. We will not eventually use this variable, but for a while, just to use it. So in this case, now our right-hand side term can be further simplified. Okay, why? So let me just do it together with you. In this case, what we do is just to consider this first term and the third term. So these are just combined together, and the common factor is taken as this one, q y infinity and kbt. Then what happens to this first term? Or of course, since common factor is taken, so we have to have something like this: exponential minus kbt q and phi minus phi infinity comes in here. And of course, this third term just gives minus 1 because third term itself pops up here. So we have just minus 1. So, you know, this is quite lengthy. However, due to our new variable phi bar, it can be just written as phi bar. That's the reason why when you have a look at this expression, we have a relatively simple form, and you know that this is just a combination of our first term and third term. You can easily guess that this term is also a combination of second term and fourth term. Okay, so we have this expression. But before uh, move, moving to the next page, I wanted to stress this information. Here we have a certain exponential function for our electrostatic potential. But here we have two boxes, red boxes, and they are dependent on phi infinite. So this is just a constant and doesn't depend on position or electrostatic potential. This is just a given number. Then which one is in its magnitude large and in its magnitude small? So since phi infinity is a negative quantity due to the p-type region, so this quantity is the first quantity is very large number. So how large is it? For example, if we consider 10 to the 16 per cubic centimeter, then this value is almost corresponding to 10 to the 6. More precisely, it is corresponding to Na over intrinsic carrier density. Since this value is quite large, its inverse shown here is also quite a small number. So this is corresponding to, in this example, 10 to the minus 6. So it is corresponding to the inverse of the first one. So if we consider just the leading coefficients shown here, here, and here, of course, this term is much larger than that. So in usual case, if these curly bracket terms are comparable to each other, then obviously this first term will contribute to the right hand side mostly. However, if we have a quite large contribution from this second curly bracket term, then although we have relatively small coefficient, leading coefficient, that can be overcome by this expression, because our hope is this is related with exponential term. Okay, so I will explain it a little bit later. Okay, so anyway, what we are doing is just starting from Poisson equation and multiply certain quantity. After that, just manipulation. Nothing has changed from post-multiplication. Then we wanted to make the integration from the surface point toward positive infinity, deep the substrate. Then what will happen if we make a certain integration? Um, so in that case, our dx changes from 0 to infinity. And if we consider it as in terms of, for example, phi bar, then what will happen? This will just goes to phi s to 0. Why? Because the phi value evaluated at positive x equal to 0, that is defined as phi s. And in that case, we must evaluate it phi at infinity minus phi at infinity. So by its definition, that should vanish. So also here we have another um, integration variable. For example, d phi over dx. So if we make an integration like d phi over dx, then obviously also we have to start from the electric of the first derivative evaluated at x equal to 0 and go to number 0. Why we have number 0 here? It is only due to the boundary condition we have considered in this point. At the deep substrate, we have vanishing potential gradient. Okay, so then now by performing this job, then you can immediately find this relation can be obtained. So the intermediate steps are skipped a little bit. So please try to evaluate it. And now we have this kind of expression. So it looks quite complicated, and actually here we have 6 different terms. The first term, exponential term, and linear term, and this is constant term, and this is a linear term in terms of surface potential. Also here we have exponential term and constant term and linear term. Oh, why do we have such a kind of so many terms? So when you have a look at this one, you can easily understand. This is the origin of linear term, and this is also the the origin of linear term, and exponential terms generate exponential minus constant. Also exponential minus constant. So you can easily check the validity of this expression. Okay, so anyway, it means that by using this expression, once we know a certain variable phi sub s, then now we can calculate the d phi over dx evaluated at the surface point. So the gradient of electrostatic potential at the surface is closely related with surface potential. This is quite significant, it is only because, here we have infinitely long p-type substrate, but this relation just says that if we know surface potential and at the time, then we can immediately understand also this gradient immediately. So this is a quite a significant improvement on our understanding. Okay, so this is just rewritten or the simplified form shown here. And as I told you before, this is a surface gradient, and here we have surface potentials, and these are just constant. However, this is very large and this is very small. So, so now we have quite a beautiful expression. So let's try to draw the surface gradient as a function of a surface potential. Mm, because the right hand side only contains phi s. So once we know surface potential, calculation of this gradient is done immediately. So it is not that difficult to draw these graphs. So please try to do that. So in order to draw this specific example, I have used 4 times 10 to the 15 per cubic centimeter as accepted density, and my parameters are shown here. So of course this intrinsic carrier density really depends on the temperature, but I assumed 300 Kelvin, and the intrinsic carrier density of silicon is used here. Of course, Q and KB, they are universal constants. And please note that although I have drawn it here, but this is drawn in logarithmic scale. So 10 to the 7, 10 to the 6, 5. So we have to be careful about sign. And in this case, this is corresponding to positive sign and negative sign. So simply speaking, although here, for example, when phi s is around 0.8 volt, so this one shows that d phi over dx evaluated at 0 is quite close to 10 to the 5 volt per centimeter. However, you have to understand this is a negative sign, so we have a negative sign here. Okay, so this is just a matter of okay, presentation. So okay, so I want to stress that this equation or this relation is really general under the given structure of our MOS capacitor. Then this analytic equation or expression is really rigorous. So, since it is sometimes too complicated, so people wanted to sometimes introduce approximated expressions. For example, if we have sufficiently negative phi s, then let's just consider all of these numbers. Okay, first of all, if we have sufficiently negative numbers, then this input argument for exponential term will be quite large. Yes, this is large. And compared with this large component, for example, -1 or just a linear term doesn't make any sense. And also, this second term doesn't play any role because the leading coefficient is so small, and for negative uh, the negative input argument for this exponential, this one just approach to number 0. So what we can say is, if we have sufficiently negative input argument or surface potential, then the only thing we have to keep is, yes, this exponential term, exponential minus surface potential term. So as you can see that this is an exponential term. let's consider positive case. So positive, but its uh, uh, surface potential is not that high, then still this second term doesn't play any role, but instead of that, now this exponential term goes to zero quite rapidly, and this linear term plays significantly. So you can see that in this case, yes, we have linear term which is dominant in this domain. And if we go to sufficiently large phi s, then here you can see that this exponential term really dominant. Although its leading coefficient is so small, however, if our phi s can overcome this phi infinity, then eventually this term will be the dominant term. So here you can see that this is the expression for our sufficiently large surface potential. So in this slide, I just drawn all of three approximate expressions. This blue one, this one is the exact one, and this orange one is only for negative phi s. Yes, it shows good agreement. And this green one is corresponding to relatively small positive phi s. And you can find that this is perfectly matched for this range. And if we go to sufficiently high surface potential, then actually the behavior can be well described by our exponential function. Okay, so now you have some approximate form for each case case. So of course, then where do we have a certain, I can say, the need point between different different domains or different approximations. So it really depends, especially what is the clear cut between this part and that part. It is not that uh, clear, but anyway, for sufficiently uh, well-defined position or range, then we have a reasonably good agreement. Okay, so up to now, I just give you the way you can calculate the surface potential gradient as a function of surface potential. It looks quite good, but sometimes, or in or in most cases, we wanted to solve the opposite way. Surface potential is given, and we wanted to calculate the surface gradient. This is usually not the case. We know the surface electric field and try to find out surface potential. Then how can we do that? In this case, of course, we must use Newton method. Um, so, for example, when the surface uh, gradient is corresponding to -1 megavolt per centimeter, so then please try to calculate the phi s. This is the case. Of course, if we have these graphs, then you can find that, oh, maybe graphically somewhere around here we have surface potential corresponding to uh, minus 10 to the 6 volt per centimeter, the surface gradient. But this graph is not always available to us, and this is not the way we do in the compact model or numerical analysis. We should be able to evaluate it directly, so we must use Newton method. So in this Newton method, we just treat the function of surface potential, and this function evaluation should vanish. The function to become zero just looks like this. The difference between square of surface field gradient and yes, long terms. However, its a derivative with respect to phi s is so straightforward. Why? Because it doesn't make any sense. And also here you can see that this one vanishes and this one vanishes, and this one just gives us q over kbt. Also this one gives over q over kbt. The only remaining two terms are exponential functions, but also derivative of an exponential function with respect to the input argument is quite straightforward. So you can easily calculate the f over d phi s in this way. Now you know the function value and the sensitivity of a function value with respect to the solution variable. So now you can implement the Newton method quite easily. Although it is lengthy, but you can just type this equation, then you can make the Newton iteration. Once again, please be careful about too large update of your surface potential. For example, in my case, so I just restrict the maximum update value, the absolute sense, only up to this kBT over Q, the summer voltage. Now you have the homework number 4, and still due is September 19th, so it means that you must submit homework number 2, 3, and 4 at the same time, but I think that each of them is not that difficult, so I assume that I hope that all of you guys can submit the homework problems without much difficulty. Uh, the homework problem is like this. Just to implement a Newton method to solve this MOS capacitor problem. So doping density is just kept as 4 times 15 per cubic centimeter, and now we have 10 different surface. I made a mistake or typo here. So we have minus and minus. All of them are minus. So I wanted to ask you to calculate positive phi s value instead of negative phi s value. And anyway, we have 10 cases. Then please calculate the surface potential corresponding to these 10 surface potential gradient. And this is the answer. Now you have the answers. For example, this is corresponding to 60 minus 60 kilovolt per centimeter, and the value is slightly below 0.8 volt. So please show your numeric values, not just showing this graph, but please show the numeric value, and please specify the number of iterations you had to spend to get those solutions. Okay, so let me just summarize today's talk. As I told you before, so at the beginning of our lecture, today we have thought about one equation about MOS capacitor. What was it? That was just a Poisson equation. So by multiplying just d phi over dx, we just integrate it, and with the help of a specific form of electron density, for hole density, we were able to analytically integrate this Poisson equation. And as a result of this operation, we obtained an equation, nonlinear equation for phi sub s surface potential, and we treat it as as a unknown as a nonlinear equation, and by applying the Newton method, we obtained the numeric solution for this equation. So now it means that if we know the surface potential gradient, and now we can calculate the surface potential. This is a huge improvement from the viewpoint of our application to the MOS capacitor, and the next time by using that information we will get just voltage characteristics of MOS capacitor. Okay, so okay, thank you for your attention, and have a wonderful Thanksgiving holiday, and see you on September 19th. Thank you.